So far, we've seen how we can store integers in one of these data indexed arrays. So now let's talk about how we could store English words. So in the long term, our goal is we want to be able to support arbitrary data types. But for the moment, let's restrict ourselves to just thinking about English words. And so let's say we try and add the words cat, bee, and dog into our data structure. We need to know where do cat, bee, and dog go, right? Like which value should I set to true? So the previous idea we have only supports integers, and we need to go and do something better. That is, I have a user who expects to be able to insert bee, or cat, or dog, and we need to decide how we're going to represent, say, true false values, so that the user observes correct behavior. So the key question then really is, what is the catth element of a list? Well, here's one kind of bad idea, but an idea that pops to mind, which is, let's just use the first letter of the word as an index. So cat starts with C, and C is the third letter of the alphabet, so I'll just set this value to true. That is value 3 to true. Now the problem with this approach is that if we then ask, does the array contain chupacabra? Well, since chupacabra also starts with C, we'll get back true. And in this case, we would say that chupacabra collides with cat. The same representation is used for both words. Another problem, which we won't address in this video, but we will soon, is we can't store strings that start with, say, equals, because equals is not a letter of the alphabet. Okay, well, let's talk first about avoiding collisions. What we can do is use every single digit, and in particular, we're going to multiply each digit by a power of 27. So for example, the index of cat will be 3 times 27 squared. 3 because C is the third letter of the alphabet, and 27 squared because that's the power I chose for this. A will be 1 times 27 to the first power, and then T will be 20 times 27 to the 0th power, that is 1. So why this specific pattern? Why am I doing this? Well, we'll see this when we look at how numbers are represented in decimal. Now, I guess one thing I glossed over here is that the result of this computation will be the integer 2,234, and so that means we would go here into location 2,234 and set a true value. And in this way, we could think of position 1 as representing the letter A, 2 as position B, 3 as position C, or 3 is the position for C, 4 is the position for D, and so forth. Okay, so why am I doing this specific pattern, these powers of 27? Well, let's think about how numbers are done in decimal. So in the decimal number system, we have 10 different digits. We have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. If you want a number larger than 9, you use a sequence of digits. Okay? Well, for example, 7,091 in base 10 is nothing more than, well, it's 7 times 10 to the third, plus 0 times 10 squared, plus 9 times 10, plus 1 times 10 to the 0. And so in effect, our approach of converting strings into numbers is mimicking this behavior for base 10 numbers using decimal digits. Okay? So to see if this makes sense, I would like you to convert the word bee into a number using this powers of 27 strategy. So same basic idea, but give me the number for b just to make sure this all makes sense. All right, so b is the letter 2 and e is the letter 5. So in base 27, if we multiply all this out, we'll have 2 times 27 squared plus 5 times 27 plus 5 times 1. And that will give me the number 1,598 in base 10, and we could use that as our index into an array. Okay. Now it turns out that as long as we pick a base that is greater than or equal to 26, this algorithm will definitely give us a unique number for every possible lowercase English word or even English string. So for example, using base 27, no other words, no other strings will get this number 1,598. We will never have a collision as long as we pick this nice large base. Okay? And why is that? Well, by analogy with decimal, there's no possible way using decimal digits to write the same number in two different ways, and that is also true here. Okay? But I'll leave this proof as kind of a thing to ponder. So an optional exercise that I'm not going to go through, but you might find interesting, is trying to write the function that converts English strings to integers. So for example, a becomes 1, z becomes 26, AA is 28, and so forth. So you might try that fun, or find that fun, and if you'd like, I have the answer on the following slide. Now I'm not going to talk through this at all because I don't think the code is super interesting, though I'll say just a little bit about the main function English to int. It basically just goes through each character in the string, and it will start by multiplying the current representation of our integer by 27, so that's the power of 27 thing, and then we add the letter num for the ith character of the string. And here I have a helper method I will not describe in any way. So in the end, what we end up with is a very simple implementation. We just need this English to int method, and having it, we just simply add it to our add and contains method. And there's not much more to it, and it'll still be constant time and wonderful. However, there are still some obvious problems that we'll address in the next video.